Okay, let's talk about parallel vectors and notice something really cool that we can do with these. So let's suppose we got this vector v and another vector w. Now these vectors are parallel. One vector is longer. The w is longer than the v, but they are parallel. Notice we can tell they're parallel because they have the same slope, right? We go over 1 up 2 on this vector. Here we go over 1 up 2 over 1 up 2. So they both have a slope of 2. Now let's put these in component form, and in other words, let's move these vectors over without changing their direction so that they have the initial point at the origin. First, whoops, okay, so first I'll move over the w, okay, and notice that now we could designate that vector as being 2, 4. Notice because it goes over 2 and up 4. That's the terminal point. And we do the same thing for the v. Move it over, and that vector is now 1, 2. Now here's something interesting we could take note of about these parallel vectors. Since they point in the same direction, we just make this observation that w is simply twice what v is. In other words, if you multiply v by 2, see, 2 times 1 is 2, you get the x-coordinate of w, and 2 times 2 is 4, you get the y-coordinate. So it turns out that w is just 2 times v. Now this is a property of parallel vectors. If you have two vectors that are parallel, that's what it means. So if a is parallel to b, for example, then a is a constant multiple of b. And you could say it the other way. You could say b is a constant multiple of a. Okay, so let's see how we can use that. Let's suppose that we have this point, 5, 4. And there's a line that goes through that point, and we want the equation for that line. Well, we already know how to find the equation for that line from Algebra 1. We've got a point, we can figure out the slope. In this case, the slope is 2, so it would be easy for us to find the equation. But let's take a different approach. Let's use vectors. In other words, instead of giving the slope, instead of saying we want an equation for that line, we want an equation for the line that passes through 5, 4 that has a particular slope. Let's word it this way. We want an equation for a line that passes through the point 5, 4 and is parallel to this vector right here. This parallel to this vector 1, 2. Okay, let's proceed this way. Let's just consider another point on this line, xy. There it is right there. Now, think about a vector. Let's just consider a vector here that starts at 5, 4 and goes up to xy. And let's put that vector in component form. Now remember, this vector here is going to be parallel to this vector. So if we put it in component form, we're going to get this. X minus 5 for the first component, y minus 4 for the second, and that's equal to a multiple of the other vector because the vectors are parallel, and we'll just use t as that number, right, instead of c. So this vector is a multiple of this one. Now, the implications are, if we equate corresponding parts, x minus 5 is equal to 1t. See, if I multiply through here by t. And y minus 4 is equal to 2t. See? Now, this is a set of parametric equations that describes that line. Now, let's just note this, that I could solve for t, or I could note that t is equal to x minus 5, and just replace down here where this t is, replace it with x minus 5, and then I have y minus 4 equals 2 times x minus 5. See how this one and this one are the same. Now this is the old familiar point-slope form of a line. You give me a point and a slope, and I'll give you the equation for the line. Here's the point, x naught, y naught. The slope is m. So you can see how this works out the same way. Now, if I solve for x up here, I get the x-coordinate is t plus 5. If I solve for the y, I get the y-coordinate is 2t plus 4. Now, this is a set of parametric equations that describe that line. In other words, if you give me a t, I will give you an x and a y coordinate of a point that's on this line. That's the cool thing that we just figured out. we have another way of finding an equation for a line. Now, so let me state it generally. You've got a line that passes through a given point and is parallel to a given vector. How do you get the parametric equations that will describe that line? Just like this. This is the general way to state what we just looked at. X equals AT plus X naught. See? AT plus X naught. Y equals BT. See? B. The vector components go in front of the T, and then the points go right here at the end. Now, we could use the same approach and develop this method for 3 dimensions. So we could talk about a line in 3 dimensions. Now here's where we really need this method in 3 dimensions, because in 2 dimensions we just have a point and a slope. But when you get a line that's going through space and you talk about the slope, what in the world are you talking about? You know, in 2 dimensions you're looking at the change in y over the change in x, rise over run. But in 3 dimensions, you've got more directions than just the x and the y. You've got the z as well. And if you think about a line going through space, you know, out here in 3 dimensions, it could point all different ways, right? It's not just on a plane. So here's where we really need that vector, this method. So if you've got a point, x naught, y naught, and z naught, and it is parallel to a vector ABC, the x coordinate's going to be the same, you know, just like we did earlier. The y coordinate's the same, but now you've got the z. So there it goes. So this is the set of parametric equations for a line in space. So let's look at an example. Here's a line, here's a point in space. It's parallel to this vector. And you want the equations, a set of parametric equations that for that line. So you get, now notice, 8, that comes from the vector. It's in front of the t. And then the -2 is just from the point. The y, once again from the vector, the 9 plus 4. And then finally the z equals 3t plus 7. Okay? And that will give you an equation for the line of space. And what this means is, you give me a t value, any t value, just come up with one, and I will give you a corresponding point on that line. I can compute the x value, the y value, and the z value for a point on that line. And that is what this method will do for you.